I hope my screen is visible.
Yes, screen is visible.
शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you. I would now like to request Principal Ma'am, Dr. Lona Mukhopadhyay Ma'am, to kindly address the welcome speech. So, Ma'am, it's over to you, Ma'am.
Thank you, Jasmine. Am I audible?
Yes, ma'am. Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay. Hello, everybody. A very good evening to you all. I am Dr. Lona Mukhopadhyay, Principal of RBC College for Women, Noihati. It is my pleasure and honor to welcome Dr. Sudipta Mukherjee, Professor of Physics, Institute of Physics, Bhubaneswar, Odisha. He will be delivering his speech on a mechanical analog of spontaneous symmetry breaking. His enlightening speech will help students upgrading their knowledge and skills on the said subject. I welcome Dr. Rupali Kundumam, convener of this webinar. I also welcome the IQAC coordinator, Dr. Monica Vishwas, and Dr. Jasmeet Singh, the teacher of English of our college, and will be conducting this same webinar from the beginning to the end. Dr. Tulima De, the librarian and technical assistant of this seminar, and I also convey my best wishes to Soharto, the NTS, who has extended his technical assistance for this webinar to happen. My best wishes to him, and also not but lastly, I welcome all the participants, students, teachers present here. Without their presence, this webinar would not happen and would not be successful. In this pandemic situation, where college is closed for over more than 1.5 years, and online classes and online exams are going on. So webinar, this type of online seminar, is a virtual platform where knowledge can be exchanged, and teachers as well as students are enriched with knowledge on the subject, on their respective subjects, and also enrich themselves and increase their skills. So I hope that this seminar will be a great success, and I request all the participants present here to be present till the end of the webinar so that this webinar completes successfully. So thank you all. My best wishes to all. Have a nice time. Thank you. Over to Jasmeet.
Thanks a lot, ma'am, for this welcome address. I would now like to ask Dr. Rupali Kundumam ma'am from the Department of Physics to kindly introduce our resource person. Ma'am, Dr. Rupali Kundumam ma'am, it's over to you. Ma'am, are you there online?
Yes. Am I audible? Yes, yes.
Yes.
Am I audible?
Yes, ma'am. Yes, ma'am. You are.
Can you hear me?
Yes, ma'am. We can hear you.
Oh.
We can.
Thank you. Yes. Yes. A very good evening to all of you. At the beginning, I would like to take this platform to thank our principal madam, Dr. Lona Mukhopadhyay, for encouraging me and supporting me to organize this webinar. And I am very much grateful to our speaker today, Professor Sudipta Mukherjee, for sparing some of his time to spend some some of his time with us, even within his very busy schedule. Actually, he is one of my most favorite teachers from the Institute of Physics, where I have completed my PhD. He was not only a very good teacher, he was very much friendly to us, to all the students. The students were always allowed to enter his office to discuss any academic, even non-academic problems also. So, it is a great pleasure for me to introduce Professor Mukherjee in such an occasion. So, Professor Mukherjee, he has graduated Bhavan. He has his master's IIT. Then he joined Tata Institute of Research (TIFR) as a PhD student. From there, after his PhD, he pursued his career as a postdoctoral fellow, and he joined International Center for Theoretical Physics (ICTP PSA), Italy, as a doctoral fellow. From there, he moved to Texas A&M University, College Station, USA, and after that, he joined Institute of Theoretical Physics, Master's, then a fellow. After that, he joined as a faculty member. He joined as a member to IIT Kanpur, and from there he moved to Institute of Physics, Bhubaneswar, where he is working presently. His area of research is high energy theoretical physics, and particularly his particular interest of areas of interest of research is string theory and classical and quantum aspects of black holes and cosmology. So, we are eagerly waiting for his students' presentation, a mechanical analog of spontaneous symmetry breaking, which I think will be helpful to the students of particularly who are going to have condensed matter physics and particle physics. So, at this place, I strongly encourage the students to follow it and ask any questions. So feel free to ask any questions to the speaker. So this is all about. So now I request Professor Sudipta Mukherjee to deliver his presentation. So please, Sudipta.
Thank you, Rupali. So first of all, I'd like to thank Dr. Lona Mukhopadhyay, principal of this college, and also Dr. Rupali Kundumam for inviting me to give this talk. I enjoy presence of kids around, and I like to talk to them. Unfortunately, I'll try to do my best on this electronic platform. So thank you very much. Am I clearly audible? Because I'm going to start now.
Yes, sir, you
Yes,
are.
sir.
You are.
Yes.
Okay, good. So what I'll do is that I'll switch off my video and I'll present my pull my talk here. Okay, let's see. So can you see the write up?
No, sir. No, sir.
Okay, so let me see. Okay, just a sec. I need to present. Okay, one sec. Present now. Just wait.
Yes.
So now can you see?
Yes, sir, it's
Yes.
visible.
Yes.
So it's clearly visible. Can you see the my marker, the cursor?
Yes, sir. Yes, sir.
Okay, great. So I start. So as announced, the title of my talk is a mechanical analog of spontaneous symmetry breaking. So sometime I will address spontaneous symmetry breaking as SSB. Okay, so the aim of this talk is to introduce a toy model which exhibits spontaneous symmetry breaking. And what I'll do is that I'll try to set a comparison between this toy model and with spontaneous symmetry breaking in more complex systems. Okay, so the question first arises, why we are interested in spontaneous symmetry breaking in the first place. Okay, so as I have written here, spontaneous symmetry breaking plays a central role in contemporary physics. In fact, various different areas of physics. I will emphasize two. So in particle physics, for example, it gives masses to certain elementary particles. You know, elementary particles have certain masses. So some of those elementary particles are given masses by spontaneous symmetry breaking via what is called Higgs mechanism. So this is a bit complicated thing. I will not emphasize much on this. But what I'll emphasize is the second point, and that will be more or less the focus of this talk. So spontaneous symmetry breaking also plays role in condensed matter physics. For example, it triggers second order phase transition. So I can give you an example. Take a magnetic material, for example, and take it at a low temperature. Take a magnet, and at low temperature you see that it has a magnetic property. It has a non-zero magnetization. That's how we measure. But suppose so the magnet is made out of some material, so it will have some Curie temperature associated with it. Suppose I jack up the temperature now above Curie temperature. You know that the system will lose its magnetic property. Now this is done by this is triggered by this transition is triggered by spontaneous symmetry breaking. And now what happens is that above Curie temperature is typically mentioned as critical temperature. So above this critical temperature, system goes to a disordered phase, and the average magnetization goes to zero, and the system loses its magnetic properties. Now what happens exactly at critical temperature, many of the thermodynamic variables like susceptibility and specific heat, for example, starts behaving non-analytically. So non-analyticity means that some of them behaves in a singular manner. Something diverges. Okay, they may diverge when you are exactly at the critical temperature. So so naturally, so these are the two cases I point out. There are other cases. For example, in cosmology, spontaneous symmetry breaking has a role to play, and in various other areas of physics. So knowing that this is such an important stuff to learn, so I will try to introduce it. First, in a very simple manner, which will not capture all the properties of this mechanism, but it will capture some properties, and the example is very simple. And then I'll go over to the toy model that I'll be talking about. So I'm audible clearly?
Yes, sir.
Okay, great. So now let us consider a particle of mass m moving in one dimensional potential. So I have one direction which is level by x, and I have a potential which is minus alpha x square plus beta x to the power 4. Okay, so alpha and beta are dimension full constants, so that this is length square, and you multiply with this, it gives the dimension of potential. So all these alpha and beta have dimensions, but though they are constants. Now I'll take alpha and beta to be greater than 0. So alpha here and beta here are both greater than 0. So the kinetic energy associated with that particle is simply half m the mass dx dt whole square, right? So which I will write sometime as half m x dot square. X dot meaning that is the time derivative on x. And the potential energy, as I have written, on the same one as before. Okay, so that is the potential energy. Now what we normally do is that we construct a function called Lagrangian. Don't worry if you are not familiar with the name, I will not need it much. which is, I'll write it as L, which is simply a difference between kinetic energy and potential energy. So since kinetic energy is half mx dot square and the potential energy is what I have written earlier, so this is the total Lagrangian. Now once given the Lagrangian, what you do is that there is something called Euler-Lagrange equation. You put L in that equation, you get an equation of motion. Okay, so we don't need to know much about Euler-Lagrange equation, but just that we will be looking for equilibrium position. Equilibrium position means where x is independent of time. The particle stays there. So it's independent of time. So we'll be looking for configurations where x dot equal to 0. So if x dot equal to 0, then you see the kinetic energy part drops out. So what remains is the negative of potential energy. Okay, so essentially so this is all I need from Euler-Lagrange equation, that in that case, Euler-Lagrange equation simply reduces to variation of Lagrangian with respect to x equal to 0. Since kinetic energy is 0, so it essentially turns out to be a variation of potential energy with respect to x is 0. So this equation tells me that I should be looking for the maxima or rather extrema of potential energy. Okay, that is likely where the particle is going to stick around or going to be there in the equilibrium situation. Okay, so I don't need to do all this. This is a simple potential. I can just simply draw. So how the potential looks like? I have alpha positive and beta also positive. So I have drawn x-axis as the coordinate of the particle, that is x, and this side is the potential energy, because the kinetic energy is 0 for the equilibrium position. Now, since alpha is greater than 0, so when x is small, which this term is dominating, x square, because x to the power 4 will be even smaller, right? So the behavior near x equal to 0 will depend upon, primarily will depend upon this quantity. Now this quantity is negative, so the potential will go down. Okay. Now when x becomes little big, this term, x to the power 4 term, will start dominating, and then since beta is positive, so this will go up. So at some point it goes up, some point it's going down, so somewhere there must be a minimum. Okay. Now you notice that this potential that I am drawing, which is minus alpha x square plus beta x4, is symmetric under x going to minus x, because if you change the sign, this is square and this is fourth power, so they don't change. So the potential is symmetric under x going to minus x. That means in the positive x side, whatever I'll have, whatever the diagram, it will repeat in the negative x side. So this line will work as a mirror. So exactly the same situation here. So now you see that x equal to 0 corresponds to extrema. This one corresponds to an extrema, and this one corresponds to an extrema. Now this is going to be an unstable place, because if the particle is here, any disturbance is going to roll down either here or here. On the other hand, these are the minimum position where particle, if it's there, is going to be there. So that is going to be the equilibrium position. So now I have only one particle, it cannot take both the position. Though here potential energy is same. Okay, you see the minima here and this minima here, it touches this horizontal line. That means the potential energy corresponding to this and this, both the minima are same. So the particle is not going to be here, is either going to roll down here, because this is not a stable point, or it's going to roll down here. So now you see we started, so what I have written is that we have a degenerate minima. That means the potential energy here and here are same. The particle will occupy one of this, it cannot occupy both. Now you see we are having a different situation. I started with x going to minus x symmetry of the potential, so it's exactly same. So you cannot distinguish if you don't look at the particle, you don't distinguish between this side and this side. So that's the symmetry. But when the particle takes this position, this side is preferred, right? The symmetry gets broken. X going to minus x symmetry is broken simply by the position of the particle that it has taken. It has not gone here, so the symmetry is not there. So what we say, so I have written down here the Lagrangian again. I have done a typo error. This has to be there is a mistake here. This will be plus, and consequently this will be minus. There are two mistakes here. So you see, so this will be plus and this will be minus. So I have written down the Lagrangian here, and here is the total energy, which is half mx dot square, that's kinetic energy, plus the potential energy if you correct the mistake here with the minus sign. So this is symmetric under x going to minus x, but the symmetry is broken by the ground state. Ground state, I mean the equilibrium position of the particle. Right? When it has taken one, it has not taken the other, the symmetry is broken. So we say the symmetry is spontaneously broken. So this is how we introduce spontaneous symmetry breaking. The symmetry is present here in total energy or in the Lagrangian, but it is broken by the choice of the ground state or the choice of the equilibrium position by the particle. Okay, so I want to distinguish between spontaneously broken symmetry or an explicitly when I break a symmetry. Again, I have done a typo here. This sign should be plus. Okay, so this was my earlier Lagrangian with the plus sign here. Now suppose I add a term gamma. Gamma is another constant, and x cube. Now if I add a term x cube in the potential, so they will appear in the Lagrangian. Now you see the Lagrangian or the total energy, which will be sum of this term and this term, is not symmetric under x going to minus x, because x cube changes sign. Right? So now this is what is called explicitly breaking the symmetry. So we have broken this discrete symmetry x going to minus x by adding this term gamma x cube. When gamma is 0, I get back the symmetry. So this is the difference that has to be kept in mind. So one is spontaneously broken symmetry, which is broken by the position of the particle, and another is explicit symmetry breaking that I have broken by adding a term which doesn't respect the symmetry. Okay, so now I come to the purpose of this talk. The purpose of this talk is to construct a simple model. So I hope now spontaneous symmetry breaking is somewhat clear. It will be clearer if not now, as we go along. So the purpose of this talk is to construct a simple mechanical model which exhibits spontaneous symmetry breaking. So I'm going to construct a toy model which will have this property that ground state will break the symmetry of the Lagrangian or energy that is present. Once we understand the model, we'll draw a comparison with a paramagnetic to ferromagnetic transition that I mentioned earlier. Okay, so here are the references. The toy model that I'm going to present, I first came across, or I first encountered in class 11. In class 11, that is early 1980s, I think 82 was when I was in class 11, 80. Or yes, around that time. So we used to have the physics textbook is DPC. The full form is Datta Pal Chaudhary. So that is the book we used to follow. So in that book, there used to be a set of problems at the end of every chapter. So one of the problem was this toy model that I'm going to present. So that time I didn't realize the beauty of the model, but later, much later, I came across this paper. I ended up in it's much later. So this paper, this is a beautiful paper by Fletcher, where he discusses this model in great detail, and this appeared in a journal called American Journal of Physics, and the detail is all right. So what I'm going to do is going to follow this more or less this paper. I'll not have much new to say, but my presentation is little different from the way it has been presented in this journal. Okay, so I introduce the model. The model is called. Is everything clear so far? I mean, if there is any question, please stop me and ask. Okay. So the model is called ring and bit problem. So let me explain to you what is this ring and bit problem. So I have a ring, okay, a ring which has a radius r. Okay, so I have written it here. I have written it here. Now this is the radius r, and then I have a bit which is allowed to move along the perimeter of the ring. Okay, so I have a ring of radius r, and it's allowed to move along the perimeter of the ring. So I will assume that there is no friction between the ring and the bead. Now bead has a mass m. Okay. Now what I am doing is that the ring is kept on the table. Okay, I have not vertically on the table. I have not drawn the table plane here, but it is assumed that is kept on the kept perpendicular to the plane of the table, and there is no friction between table and the ring also. The ring. Now this vertical ring on the table, I rotate with the angular frequency omega. Okay, so I rotate about an axis which passes through the ring, but it doesn't pass through the center of the ring, but it passes through a distance a from the ring. So I hope the situation is clear. Now if you don't understand this diagram, it will be difficult to follow later. So I repeat, I have a ring with a bead sitting here which moves around the perimeter. There is a mass m, the ring has a radius r, and this ring is kept vertically on the plane of the table. Okay, the table plane I have not drawn, and I am rotating the ring about an axis passing through the ring. So this is the axis with an angular frequency omega. Okay, I hope now it's clear and there is no friction whatsoever. So the question I will ask is that as I increase omega from 0, so when it is not rotating, to a higher and higher value of omega, where the bead is going to be. Bead is going to be here. For example, if the ring is not moving, it's not rotating, the bead is going to be here. That's clear. Now suppose I increase omega slowly, the bead is going to go somewhere here or is going to stick here. Okay, so this is the question I'm asking. So the question I'm asking again, I repeat, what will be the position of the bead as I tune omega? That means as I change omega from, let's say, 0 to a higher value. So the position of the bead has to be figured out by free body diagram. So I assume that suppose the equilibrium position of the bead is somewhere here, which makes an angle theta with the radius, this vertical line passing through the center. So it makes an angle theta. So what are the force acting on that? So the force on the particle is the bead is due to this mass, which is m times g. G is the acceleration due to gravity. It's a fixed number, and then there is a perpendicular force which is normal, so which I call n, which has two components. One vertical component. If this is theta, then this angle is also theta. So vertical component is n cos theta, and it has a horizontal component which is n sin theta, right? Because this angle is theta and this is hypotenuse, so this is the n cos theta. This direction of the force in the normal component. So the force balanced equilibrium, in the equilibrium the force has to balance. So vertical components, which is n cos theta, has to balance mg. So that will be for the first condition. And the second component, second thing is the horizontal force has to be balanced. So I have n cos theta, n sin theta here, the horizontal component of normal force. And there is a, since this guy is rotating around this axis, it's rotating like this. So there will be a centrifugal force, which is m omega square times the distance of the particle from this axis, because along this, from this axis it's moving. So this distance is going to be, this is r, this is going to be r sin theta, and then this distance is a, so this is going to be r sin theta plus a. So the force this time, this is called, sometimes called fictitious force, that is also called centrifugal force. This is called going to be m omega square times the distance from the rotating axis and of the particle distance from the bead distance from the rotating axis through which it is rotating, and that is r sin theta plus a. So this has to balance the n sin theta component. So this will be the at the condition in the equilibrium condition. Now we need to solve these two equations to find theta. So that will give you equilibrium positions, right? So now what I do, I get rid of this n, which is the normal force, because I don't know about those forces, by dividing one by other. So I divide this equation by that equation, so it becomes sin theta by cos theta equal to this m cancels off when I divide. So it's going to be omega square by g r sin theta plus a. So this r sin theta plus a appears here. Now let us first take the simplest case. Let us take that a equal to 0. That means I am rotating this from the axis which is passing through the center. So a is 0. So that is the first case I am taking. So in that case it becomes sin theta by cos theta equal to omega square r sin theta by g. So sin theta is going to be omega square r divided by g sin theta cos theta. So this theta has to solve this equation. Alright. So this is what I have written here, sin theta equal to beta sin theta cos theta, where beta I have defined is omega square r by g. So this beta is this constant. So this, remember this definition, this quantity beta is going to play a crucial role. So what are the components that is varying in beta? As I increase omega, beta increases. Because r and g are constant. This is the radius of the circle and g is the attraction due to gravity. The g. So what are the solutions of the equation of motion? So the one solution is clear, right? Theta equal to 0. Both sides are 0. Sin 0 is 0, cos theta, sin theta, this is 0. So theta equal to 0 always is a solution, regardless what beta is. That is what value of omega I have chosen. There is another solution when I cancel sin theta and cos theta becomes 1 over beta. So this is also a solution, right? So cos theta is 1 over beta means that there can be two values of theta. Cos theta is symmetric under theta going to minus theta, right? So there could be two solutions of theta, that is given by theta equal to plus minus cos inverse 1 over beta, right? Take the inverse of that and that gives you theta. Now you see cos theta has an upper limit 1. It varies from 0 to 1. So this solution is available only when beta is larger than 1, because then it will become fraction or equal to 1 or fraction. So then only this solution is available. So for that solution to be available, this theta is of course non-zero and this theta is 0. This is one solution, this is the other. So this solution to be available, beta has to be greater than equals 1. So beta is greater than equals 1 means from our definition m square rg has to be greater than equal to 1. So so then it will happen if omega is greater than root square root g by r. G by r is a constant. Given the ring, the radius is fixed, so root over g by r is a fixed constant. So I call it omega c. C stands for critical. So if omega is more than omega critical, this guy is going to be more than 1. If this guy is more than 1, beta is more than 1, then this cos theta is less than 1 or equal to 1. So then theta and non-zero theta value is available. So here is the summary so far. We see that possible equilibrium position corresponds to omega is less than omega c. Theta, when it is omega less than omega c, theta equal to 0 is the only solution because this is not available. 1 over beta is then greater than 1. But omega greater than omega c, there are three solutions available. Theta equal to 0, theta equal to plus minus cos inverse 1 over beta. So here some clarification of what I mean by plus minus. Cos is plus minus this. Let me go to the figure. So this is theta. Okay, so another solution might be, the ball might be plus minus theta means the ball might be exactly symmetric position somewhere here. Okay, so this will be like a minus theta. You can call it minus theta or you can call it 360 degree minus theta if this is theta. So both will be equivalent. So I will call, when I am writing minus theta, that means the angle is from this side. Theta angle is from this side. So this is what the meaning of plus minus. So there are these two possible. Now the question is, when omega greater than omega c, I have three solutions. Which one corresponds to the minimum? Okay, are all minimum or there can be maximum also, or the potential. Okay, so to look at that, I go exactly as we did in the beginning. I try to understand what is the kinetic energy and potential energy of the bead. So the bead, if you just look at, this bead can move from along this perimeter, so that will change theta. So there will be a kinetic energy half m r square theta dot square, because it's moving along this line. Theta dot is like an angular change in angular the angle with time. So there will be a term which is half m r square theta dot square. But you see this guy, because the whole ring is rotating, this guy also is rotating like this. Okay, so there will be a contribution from there, there also. So the contribution, kinetic energy contribution, there will be two terms. One is due to the motion of the bead along the ring that I said, and this is due to the rotation of the ring. So it will be half m omega square. R square r sine theta is the distance from the axis. Now it is moving with a equal to 0, so it's moving rotating around this axis, and this line is just r sine theta. So this distance is r sine theta. So this is this term, half m omega square r square sine square. So there are two terms here. Now there will be potential energy, because the rim is here. Now you can define your potential 0. It's up to your choice. So I define my potential energy if the bead is at the center 0. You may as well define the potential energy of the bead here to be 0. This will all differ by a constant. The differing by a constant will not change the physics. Okay, so I will define for simplicity that potential energy when this guy is here, the bead is here, suppose, is 0. So the bead is now here, so it has gone down this distance, which is r cos theta. So the potential energy contribution will be minus mgr cos theta. Minus because it has gone down. Had it gone up, it will be plus. So that will be the, so Lagrange here is difference between kinetic energy and potential energy. So if I write down, this is the kinetic energy part, and then minus of minus mgr cos theta, that makes it plus mgr cos theta. Now I would like to find out the equilibrium position. The equilibrium position, we have already seen that equilibrium position is going to be one of these, or maybe many of these. So let's see. So in the equilibrium position, theta dot equal to 0, because it doesn't move, so theta doesn't change with time, so this guy goes away. So what I require from Euler-Lagrange equation as before, I need to minimize the phi effective, I call it phi effective, the effective potential energy, which has two terms now, one coming from kinetic energy and one from this. So L is minus of V effective, so this term goes away, so I'll write V effective as minus m r square omega square sine square theta minus mgr cos theta. Okay, so this is what I am going to minimize, or I am going to see the nature of this potential, where the bead is going to be, I mean the extrema of this potential. So I will do it in such a manner that it has an analogy. I could have plotted this whole thing as a function of theta. Given r and g and m are all constants, I pick the values and plot it. But I will do it in a manner which will be helpful for us to compare it with the paramagnetic to ferromagnetic transitions, where also some sort of similar phenomena takes place. So imagine omega is just greater than or just less than, I have written greater, but it could be just less than omega c. So it's little less than omega c or very little greater than omega c. So in this case, let us look at cos theta. Cos theta is, for this non-zero solution, cos theta has to be 1 over beta. So beta is omega square by omega c square. Okay, if you just look at, this is beta, omega square is here, and I have defined root over g by r as omega c. So this will, I can write as omega square by omega c square. Okay. So beta is omega square by omega c square, where omega c square is this quantity I have written again. So if omega is just greater than omega c or less than omega c, beta will be just greater than 1 or just less than 1. So if beta is just greater than 1 or less than 1, theta will be very small, because if it is just less than 1, then theta will be 0, from which it will not be a solution of this equation. But there is another solution you remember, which is theta equal to 0. So this will be the theta equal to 0. That's the only possible solution. But if omega is just little greater than 1, so theta is again small, because beta is just little greater than 1, theta is again small, so I should be able to expand cos theta and sin theta in the potential as a power of theta. So what I do is that I divide by irrelevant this constant. Dividing a potential by constant or adding some constant to the potential doesn't change the physics, because extrema will depend upon derivative of that potential. To find the extrema, I have to take difference, I have to differentiate, and constant will not change the physics of it. So I simplify, I actually define V effective by mgr. I divide this quantity by mgr. So what this coefficient divided by mgr can be written in terms of beta. Okay, so if I expand this, cos theta is this, sin theta is here. So I simplify and write this expanded form as this. I don't take higher powers because theta is small. So I kept two terms. One is theta, first two terms. One is theta square and theta to the power 4. Now you see the potential is symmetric under theta going to minus theta. I remind you here. So this is sine square theta. Though sine theta changes the sine square theta doesn't. And cos theta is an even function of theta. Theta going to minus theta is not going to change the sign. So V effective is theta square is symmetric under theta. So there cannot be any term which is linear in theta or theta cube or the odd powers. Then it will not be power symmetric under theta going to minus theta. So you see that we have theta square term and theta 4 terms, comes from the fact that the effective potential is symmetric under theta going to minus theta. Okay, so I hope this part, up to this is clear. So I take this one, this side, so I just add a constant. Again I say that adding a constant with the potential will not change the physics. So then it is half 1 minus beta theta square plus this theta 4 term. I neglect the higher powers because theta is small. So I have written down again the same thing here. Now interestingly note that this coefficient of theta square term changes sign as beta varies from little less than 1 to little more than 1. So as I increase omega, little more than omega c, beta becomes more than 1. Okay, so when beta becomes more than 1, this guy becomes negative. And when beta is less than 1, when theta is little less than 1, beta is less than 1. When omega is little less than omega c, beta is little less than 1. So this term is positive. So this term changes sign as beta crosses this critical value, which is beta equal to 1. On the other hand, I am looking at beta equal to little less than 1 or greater than 1. So this term is always positive. So this coefficient is always positive, coefficient of theta 4, but this guy changes sign. Is that clear? Beta less than 1, this is positive. Beta greater than 1, this is negative. So omega less than omega c, this will be positive. And omega greater than omega c, this will be negative. So let us just plot the graph. I have a simple graph which depends on theta square and theta 4. And let's plot this. So I am plotting, this side is my y-axis, and I plot with respect to theta. So as I said, the theta is when very, very small, this term is going to dominate. So now if beta is less than 1, this guy is positive. So the potential will rise. As theta increases, potential will rise. And when theta is little more, then this guy is going to dominate because this is theta 4. So it's going to rise further because this coefficient is positive. So again, theta going to minus theta, symmetry tells me that it's going to happen, same is going to happen this side. So we see that when beta less than 1, that is omega, that angular frequency is less than omega c, this is, there is a minimum here, and the bead is going to be here, and this minima corresponds to theta equal to 0. So what we understand is that going back here, that when omega is less than omega c, theta equal to 0 is the minimum. The question is what happens when omega greater than equal to omega c. So in the ring bit diagram, the bit being here corresponds to the bit being here, theta equal to 0. That will correspond to theta equal to 0. Now when beta greater than 1, this guy changes sign. So it becomes negative and this remains still positive. So since this guy is negative, for small theta, this quantity starts going down. So what happens is that this guy goes down, but this is dominated by theta 4 term, which is still positive, has a positive coefficient. So this grows. So this grows means there must be somewhere minimum here, which is less than, which has a less V effective value than it, the bit had the bit been here, because it is theta equal to 0 and this is some non-zero theta. So the same is going to happen here. So the bit is going to be either at theta not equal to 0 or theta not equal to theta equal to minus theta not or theta equal to minus theta. That in the original diagram is going to be, the bit is going to be either here at some non-zero theta naught, or the bit is going to be here some minus theta naught. So it will be either here or here, not here. Okay, when omega is, this omega is more than omega c, but because that will correspond to, this corresponds to a maximum, local maximum of the V effective. Okay, so now you see you can find out theta naught simply minimizing, looking at the minimum of this potential, and that theta naught corresponds to this value, because V only depends upon beta, so the theta naught value will also depend upon only V. So it turns out that this is the quantity. Now notice that when beta is less than 1, this becomes imaginary, so this doesn't exist. So only thing will exist is theta equal to 0, as seen in the potential, that there is no other minimum. This is the only minimum. Alright? So let me recapitulate, say it again. So I had this Lagrangian or correspondingly total energy, which will be sum of potential and kinetic energy. This is symmetric under theta going to theta minus theta. So in a small theta expansion, so okay, so is it's small theta expansion. So I expanded in theta since L has this symmetry. Potential, effective potential, which is the contribution minus of this, will also have this symmetry, and this is symmetric anyway. Theta dot square has a square here. So if the particle is here, that when beta less than 1, theta equal to 0, this is perfectly symmetric, theta going to minus theta. So equilibrium position of the particle preserves theta going to minus theta symmetry, because it is at theta equal to 0. So this is called symmetry preserving phase. Now if I look at omega greater than omega c, then beta greater than 1, the potential looks like this. Theta equal to 0 is no longer a minimum position. It will be either here or here, not in both the places. So the bit will be either in this theta naught, minimum position corresponds to theta naught, or minus theta naught on the other side of the rotating axis. So that is what it will happen. Either it will go here or it will go here, not in both the places. So the position of the equilibrium position will break theta going to minus theta symmetry, because suppose it is here, is not symmetric under theta going to theta. You can see that theta going to minus theta symmetry will be broken by the position of the particle. It has chosen one side. So this is what is spontaneous symmetry break. The symmetry theta going to minus theta, which is a discrete symmetry here. Normally one talks about continuous symmetry, but for a simple setup, I have taken this discrete symmetry, theta going to minus theta. So that is broken by the position of the ground state, and that is the symmetry broken phase. So this is what, in a very simple example, toy example, is spontaneous symmetry break. Okay, so now I'll change my direction. I have little. I have about 6-7 minutes, so I'll go to change direction, and I'm going to consider the phenomena with a magnetic material. Okay, I'll have to simplify things. It's a many body system. Their properties are combination of atoms and molecules that make this material. But I'll try to bring out some analogy with the system toy model that I have just talked about. Okay, so I just tell you again that going back to the picture, basic picture, that again I will tell you when omega is less than omega c, the particle, the bead is going to be here, that is theta equal to 0. If omega is greater than omega c, this is no longer an available position because this will correspond to maxima. The bead will be either this side at theta naught, that is and other or this side, that will be minus theta naught. Okay, some non-zero value, and that is given by, this value is given by here, either this value or minus of this value. And this value increases as I increase beta. So as I increase omega, beyond omega c, slowly this value will increase. The potential will change, its minimum position will change. It will come to some other value of theta, and that theta naught will be larger than this theta. So this is what is going to happen. So keeping that in mind, let us go. Okay, so I just wanted to mention one little more thing. So I just wanted to also say that what is explicit symmetry breaking in this context. Explicit symmetry breaking will be, I am rotating it off the center axis by a distance a. Now what will happen? There will be a term, earlier it was a kinetic energy had two pieces. One is theta dot square proportional to theta dot square, and one is proportional to r square sine square theta, because this distance then will be rotated from the rotating axis will be r sine theta. Now it is rotating from here, so this term will be r sine theta plus this distance a, so that will be this distance. Okay, so now there is going to be a term like this. Forget about the other terms, are going to be same. So if I just expand this guy out, there will be a linear term in sine theta, because it's a plus b whole square, so there will be a linear term in sine theta. And this linear term doesn't preserve theta going to minus theta, because it changes sign. As I make theta going to minus theta, sine theta will go to minus sine theta. So L doesn't remain invariant under theta going to minus theta. So the V effective, which is minus of this quantity, this also will change sign, will not remain same, because this will involve a linear term is sine theta. So this will be like an explicit symmetry breaking. I am rotating it off center. So you can see from the diagram that this side is, since it's rotating from this side, theta going to minus theta symmetry, that is going from this side to this side, is broken. So that shows up here from the linear term in theta. So now I have given that, so this will be like an example of explicit symmetry breaking. So now I am going to go and do a quick comparison with paramagnetic ferromagnetic transition in magnetic materials and our toy model. I won't be able to do a justice to the fascinating area of this transition, but I'll be very brief. So I take a magnet, as I said, I heat up it above the QD temperature of that material. Suppose I have a magnet of some alloy of iron and cobalt nickel. So it will have some QD temperature associated with that alloy, which is pretty high. For iron is like I don't know, 700, little more than 700 degrees centigrade. So if I heat that up above this temperature, it changes material to material. If I heat the system, magnetic properties are lost, or the magnetic property is lost. In particular, the magnetic property is particularly measured by quantity called magnetization. This magnetization will be non-zero if T is less than Tc. Tc is QD temperature, or sometimes I'll call critical temperature. So if it is less than Tc, it will have some magnetic properties, and that will show up in non-zero values of magnetization. If it is T is greater than Tc, the magnetization will be 0, and typically it is called a disordered state. So when the temperature is less than Tc, we'll call it an ordered state with a non-zero magnetization. And if the temperature is greater than Tc, we'll call it a disordered state with the average magnetization being 0, because the system has lost its magnetic properties. So if I draw the diagram, a very crude diagram will look like this. This side I have plotted magnetization, and this side I plotted temperature. The temperature, if it crosses somewhere here, which is greater than Tc, the critical temperature or QD temperature of that material, then the magnetization is going to be 0. So it's going to lie on this line, on x-axis itself. If I go little less than Tc, it's going to increase and it's going to reach to a finite value at t equal to 0. Okay, so this is a very crude diagram of behavior of magnetization. So what happens is rotational. What happens is if I come down from higher temperature to lower temperature crossing Tc, there is a spontaneous breaking of rotational symmetry. Okay, I'm talking about what we talked about in the toy model is breaking of a discrete theta going to minus theta symmetry. But what actually happens is that some rotational symmetry gets broken, which is associated to the directions of these small atomic dipoles that give rise to this effective magnetization. So the symmetry preserved phase will be T greater than Tc phase. The disordered phase will have rotational symmetry because there is no the magnetization has not taken a direction. And otherwise, if T is less than Tc, there will be a direction taken, so that will break rotational symmetry. So I will not go further on this. I'll try to do a comparison between our system and the magnetic material that I have talked about as I cross the temperature around Tc. So this will be my last part. I'll take just 2 minutes more. So I have done a comparison here. Is the first is mechanical model, the variables in the mechanical model, and the magnetic system. Though here is the rotational symmetry gets broken spontaneously, but I'll still compare with both two. Here, keeping the mind that here is a discrete symmetry broken, and here a rotational symmetry gets broken spontaneously. But the analogy goes as follows. In the magnetic system, there is an order parameter. When m equal to 0, we are in a disordered phase. And when m is not equal to 0, that is T less than Tc, I am in ordered phase because there is a non-zero magnetization. It takes some direction. So in the more mechanical model, it should be compared with theta. Theta is the order parameter. In a sense, that will be clear later. It will be clear soon. So this order parameter here in magnetic system changes from 0 to non-zero or non-zero to 0 as I tune the external temperature T. Here the angle theta, which at some point is 0, at some point is non-zero, depends upon the choice of omega. When omega is less than omega c, theta has 0 value. When omega is greater than omega c, theta has non-zero value. So omega has to be compared with the temperature of the magnetic system. This is this analogy I'm trying to bring out. The critical point, which is the Curie temperature of the material, which changes material to material, should be compared with omega c, which I have defined as square root g by m. So Tc here depends upon the material. As you change the materials, the Tc will change. Critical temperature changes or Curie temperature changes. Here also, as I change the radius of the circle, r changes, and consequently omega c changes. Okay, so I'm changing from the ring from one ring to another, which has a different radius. So omega c, value of omega c, which is square root g by r, will change. So here I come here, symmetry preserving phase is the disordered phase. When T is greater than Tc, that is the high temperature phase where m equals 0. And the symmetric phase in the mechanical model, preserving phase, is omega less than omega c, opposite to that, when theta, minimum position of the bed is theta equal to 0, which is symmetry preserving phase. On the other hand, symmetry broken phase in the magnetic system is T less than Tc because magnetization picks up a direction, breaking the rotational symmetry. In the mechanical model that we are talking about, or in the toy model that we are talking about, it's omega greater than omega c, is the opposite side, where I have theta will pick up a non-zero value, equivalently m will have a non-zero value. But here it happens in lower temperature, here it will happen in a higher frequency. So here, in this case, I can have so this is so far for spontaneous symmetry breaking. I can have explicit symmetry breaking in both cases. In here, I told explicit symmetry breaking corresponds to off-center rotation of the ring. Here, the explicit symmetry breaking will be put the material in an external magnetic field. So I have an external magnetic field. I have kept the magnetic system in that magnetic field. Now magnetic field has picked up, the external magnetic field has some direction. So all the directions are not equivalent. So by turning on an external magnetic field, I have broken the rotational symmetry because this magnetic system has picked up, external magnetic field has picked up a direction. So that will be equivalent to explicitly breaking the symmetry, the spontaneously breaking the symmetry. Here, the off-center rotation will bring the symmetry. I hope the analogy is more or less clear. I'm just not saying that this is all in the magnetic system, but this is a crude analogy between these two models. Very, very crude analogy. I hope it will be useful for you when you really learn magnetic systems and go back to my the toy model that I have discussed and try to set up relook at the analogy that I have presented. So with this, I think I will stop. And if you have any question, I'll be happy to answer.
Thanks a lot, sir, for clarifying this topic. I think we have certain questions. I would like to take some questions. I think there is one question that has come from Kaushik Pal, sir. His question is: sin theta is non-linear variation itself. Is it causing symmetry breaking?
No, see, when we are looking at equilibrium positions, theta is not varying. So equilibrium position means theta is independent of time. Theta is independent of time means that the beat is going to be there. So this non-linearity or whatever that may creep in, that doesn't bother us as long as we are looking at the equilibrium position. Is that good? Could I answer the question?
If Kaushik Pal sir is here, are you there, sir? Kaushik Pal sir, have you got your answer? Okay, he has got his answer, sir. If there are any more questions, kindly you can unmute yourself and ask your question.
In fact, if you find questions or you don't understand when you think about it later, Rupali has my email address and Principal Ma'am has my email address. Just take from either of them and send me emails with your questions. I will be happy to answer.
Sir, I am just one question, but that is not related to your subject because my subject is chemistry.
Okay.
So phase change, that is the system, that is maybe example of symmetry breaking.
I mean, yeah. When, for example, if you take liquid vapor transition, for example, that is not symmetry breaking. That's called first order transition. But there is a critical point in the phase diagram where a second order phase transition takes place, and where something called susceptibility or specific is some second derivative of free energy that we in physics call it. Will show singularity or discontinuity and things like that. So that will be like a symmetry broken. So like ordinary water vapor transition or ice melting to water is not the transition that I'm talking about here. That will be more like a first order transition. So there symmetry breaking doesn't take place. But in the critical point of a phase diagram of water vapor, there will be a yes, symmetry breaking, yes.
Oh, thank you, sir.
Okay, no problem.
Okay. I suppose we have no more questions for now. Participants can email their questions to sir. And now I would like to request our IQAC coordinator, Dr. Monica Vishwash ma'am, to kindly present the vote of thanks. Ma'am, it's over to you. Dr. Monica Vishwash ma'am, are you there online?
Yeah.
Okay.
Good evening, everyone. Good evening, our principal madam, our respected speaker, Professor Sudipta Mukherjee, our teachers who are present in this webinar, as well as other participants, our students and those who are not our students. I thank our principal, Dr. Lorna Mukhopadhyay, for her active support in organizing such webinars. She has always encouraged and inspired us in our academic pursuits. Secondly, I thank our eminent speaker, Professor Sudipta Mukherjee, Institute of Physics,
as Rupali had earlier mentioned, his excellent academic career. His speech on spontaneous symmetry breaking was very lucid and informative, and I'm sure it has been very interesting to our students, specifically for the Department of Physics. I thank Rupali Kundu from our Physics Department for organizing such a webinar. It was really very informative. And I thank all the participants, especially our students, and my special thank to our technical support team, Dr. Jasmeet Singh, Dr. Tulima De, and Shohat Roy. Thank you.
Thanks. Okay.
Thank you, Monica.
Thank you. With this, we come to the end of our session. Hope everyone had a wonderful session. We will meet soon again. Thank you, everyone. Thank you. We end our session here.
Okay, thank you. Bye-bye.
Thank you, sir. Thank you, sir.
Thank you, sir. Bye-bye.